Hello Year 11, this is the Combined Science Physics Foundation Paper 1 Masterclass video. If you're not Combined Science or you're not Foundation, make sure you click on the correct video or go to the right classroom. Okay, so this is for Combined Science Physics Paper 1. It's important that you look at the right video because the masterclass is going to focus on the content that we know is going to be in your paper, so the advanced information. Now the paper is 75 minutes long, there's 70 marks, so it's about a mark a minute. Okay, if you're not marking at that kind of pace, you're not going to answer all the questions. So that's what you're kind of aim for, about a mark a minute. I'll give you a little bit of time at the end to do any final checks. Okay, now this is going to work with red slides and green slides. Now the red slides, they're slides where you listen and you read. Okay, a lot of the slides are going to be example questions where you're trying to find and fix a mistake. Okay, it's not all just going to be content. I want to really highlight the common problems that students will come across in their paper, the common mistakes, the common places where they mess up and miss some easy marks. That's what we're going to focus on. So when the slides are red, you need to listen, you need to be focused on what we're doing. When the slides are green, that's your chance to reflect and write down and fix those mistakes. Okay, that's your chance to maybe talk to the person next to you if it's warranted. Okay, but that's your time to reflect and write. So the teacher who's with you or yourself, you're going to be pausing the video at that point when I say in the video, and that's the point where you're going to be reflecting and writing and doing the answers. That's the bit where it's active. Okay, so red, we're listening. Green, we're doing. Okay, now this is the advanced information that you've been given. You should already have seen this a lot of times. Your paper is going to have a big focus on energy changes. It's going to have a focus on global energy resources, current potential difference resistance, changes of state and the particle model, atoms and nuclear radiation. There's two possible required practicals that will be assessed. They will both be assessed in some way, but we don't know how many marks you're going to get for those practicals. It might be that you're only going to get 1 mark for the IV characteristics practical. It might be 10 marks. We don't know the weighting, but we know that at some point in the paper they will be assessed in some way. What's not on the paper is anything on domestic uses and safety. Okay, nothing on the particle model with a focus on pressure. So that's stuff like the gas laws, it's all that stuff, not on the paper. Same with atoms and isotopes. Okay, so these slides we're going to focus on misconceptions and problems that I don't want you to do in the paper. Okay, so our first green slide, we've got a question on gravitational potential energy. Okay, we've got a toaster, it's toasted the bread and a spring is released, and we're trying to calculate the change in height that the bread gets to once it springs up. Okay, so pause the video here, find the mistake. Okay, hopefully you've spotted where the mistake is. So the mistake is that we didn't substitute properly. Okay, we didn't put the correct number in the correct place in the equation. We've got the equation right, but we didn't substitute correctly. Okay, so we really need to be careful and make sure that, for instance, the gravitational potential energy goes into the energy, that the mass goes into the mass, that gravity goes into gravity. Okay, we need to make sure we're substituting the correct numbers into the right place in the equation. Okay, if we don't do that, we're not going to get the marks. Okay, so if we look at the correct version, we write down the equation, then we rearrange. Okay, so we put the substitute in, we put the numbers into the right spots, then we rearrange to find out what the height is. Okay, so the change in height should be 0.1 meters. Okay, write the equation, substitute the numbers, then rearrange, find the answer, use your calculator, get the answer. Okay, now it's important that we pick the right equation. Okay, and a way you can do that, I think that's really effective, is if you highlight or underline or box the relevant information in the question. So in this case, I've highlighted gravitational potential energy, mass, gravitational field strength, and height. And then I've highlighted those things, or I've underlined those things on your equation sheet. Okay, I go through each equation in turn until I found the correct equation. I know that it's not kinetic energy because I don't have kinetic energy. I don't have speed. I do have mass, but that's the only thing I've got. Okay, it's important that you're able to pick the right equation. Okay, so your next job, you need to choose the correct equation from the equation sheet. We're given 3 example questions. You're given energy transferred, time, you have to calculate power. Choose the correct equation. So pause the video here until we found those correct equations. Okay, so we're given energy transferred, time and power. We look, kinetic energy, mass and speed. It's not that equation. Elastic potential energy, spring constant, extension. It's not that equation. Gravitational potential energy, mass, gravitational force strength. It's not that equation. Change in thermal energy, mass, specific capacity, temperature change. It's not that one. Power. Oh, we've got power. Yes, power is correct. Energy transferred. We're given energy transferred, and time. So these 3 things, we're given 2 of them. We need to find the third. That's going to be the correct equation. Go through the equations just like that. Make sure you choose the right one. It's especially important when we get to the equations using electricity, because a lot of them are quite similar. Okay, so for instance, when we're given potential difference, resistance and current, we've got 4 equations that have current in. Okay, we've got 4. But I know it's not, for instance, charge flow equals current times time, because I don't have charge flow, I don't have time. Okay, so make sure you use the correct equation. There's lots of marks to be had. Okay, next. This question has lots of problems in. Okay, it's 6 marks, and this student gets none. Okay, you need to spot the mistake. You need to fix it. Pause the video here. Okay, so this is a tricky question. Okay, a lot of the time students will have the correct answers in their heads. They've got the right knowledge, but the way they're giving that information to the examiner doesn't get you the marks. So first, burning wood in a wood burning stove like this to get a hot tub hot. Okay, it is a renewable fuel and it is biofuel. So a renewable biofuel would be the correct answer. So this is wrong. The fuel is eco-friendly. Eco-friendly doesn't mean anything. Okay, you need to be specific. Why is it good for the environment? What would be a good part of the environmental impact? Why is it good? Okay, giving out pollution, be specific. What type of pollution? Okay, it doesn't give out nuclear waste. What type of pollution does it give out? Part C, this is difficult. Okay, so describe the change to the store of energy of the wood, pipe and water as the water is heated. Now, for wood, the chemical energy was transferred to heat. That is true. Chemical energy in the wood is transferred into a thermal store of energy. But the question asks for the change. So when you see change, you need to think, does it go up, does it go down, or does it stay the same? So for wood, the chemical store decreases. For the pipe, the thermal store increases, it gets hotter. For water, the thermal store increases, it gets hotter. Okay, the important word is change. When you see it, you have to be ready to say if it goes up, goes down, or stays the same. Okay, next question is tricky. It's on specific heat capacity. I think this has got a very good chance of coming up. Okay, we've been given a mass, a temperature change, and a change in thermal energy, and we need to calculate the specific heat capacity. Okay, you need to try and spot the mistake. Think about what you do first. I first substitute, then I rearrange, then I find the answer. Try and fix it. Pause the video here. Okay, hopefully we've spotted that we've got another rearranging error. Okay, the specific heat capacity doesn't equal the change in energy times the mass divided by the temperature change. This is wrong. So when we substitute our numbers in, we get no marks. There's no error carried forward marks because the examiner can't be sure if it's just a substitution error or you don't know what each individual thing is. So you need to be really careful. You need to substitute first, then you can simplify this, then you can rearrange, then we can get the answer. 1250 joules per kilogram degrees Celsius. Okay, now that brings us on to our specific heat capacity practical. So I have 4 little panels here about the specific heat capacity practical. This will come up in some way. Now I've blocked out the different pieces of equipment I would use to find the specific capacity of this aluminium block. Okay, your job is to try and write down what those pieces of equipment are and what they measure. Okay, now instead of using these 3 bits of kit, you could use a joule meter instead. The joule meter directly measures energy. Okay, you could improve it by adding insulation somewhere. Where would you add insulation? Okay, here we've got the specific capacity equation. You need to rearrange it for specific capacity. What do you get left? What's under this box here? Okay, I've got a brief method outlined here of how I would use this equipment. Have it a read, see if you can make it better. Okay, see if you could make it better. Think about numbers. We've also got a little example question here that if we were using these pieces of information, how would I find the energy transferred? There's a current of 2 amps, there's a potential difference of 6 volts, and the heater's on for 5 minutes. How would I find the energy transferred? So pause the video here, try and fill in the missing holes. Okay, so we've got a thermometer, a heater, a voltmeter, a power supply, and ammeter. Thermometer we use to measure temperature. Heater uses to supply the aluminium block with heat energy. Voltmeter measures the potential difference of the heater. The ammeter measures the current travelling through the heater. The power supply powers the heater. Okay, we could add insulation around the aluminium block, so we're keeping that heat energy we're transferring in the block rather than heating the room that it's in. Okay, here's the correct rearrange for specific heat capacity. The change in energy, all divided by the mass times by the change in temperature. And the energy we're transferring, if we have a 2 amp current and a 6 volt potential difference, that's on for 5 minutes. Okay, we don't use 5, we times it by 60 to change it into seconds. So do 6 times 2 times by 5 times 60 to get 3,600 joules. Okay. Right, next we're looking at the IV graph. We're quite practical. Here we've got a simple circuit. We've got the standard test circuit. Okay, you need to say what each of these components is and what it's used for. We've got the 3 types of graph that we can produce using IV characteristic, using plotting I and V, plotting the current and the potential difference. What do those 2 other graphs look like? What's my missing word under here? What? Okay, how can you describe that the resistor obeys Ohm's law here? What's my missing detail about what the experiment shows? Okay, so try and fill in these missing bits and pieces. Pause the video here. So we've got an ammeter, we've got the component, the test component, we've got the voltmeter, and we've got the variable resistor. The ammeter we use to measure the current. The voltmeter we use to measure the potential difference. The variable resistor we use to control the current that's flowing through the component. We change the resistance of the circuit, we change the total current flowing through it. Okay, that allows us to plot out our 3 graphs. We've got this first graph, it is directly proportional, it obeys Ohm's law. The steeper it is, the lower the resistance. Okay, we've got a filament bulb, it does not obey Ohm's law. Okay, it is not a straight line graph. Okay, when it heats up, the resistance increases. It gets hotter, the resistance goes up. The diode does not obey Ohm's law. It is not a straight line that goes through 0. It is not directly proportional. It only lets the current flow in one direction. So when we've got a negative potential difference, the resistance is incredibly high. So it doesn't let any current flow through. Okay. Next, we have a diagram. It shows a bowl used for making ice cream. So we've got this outer plastic surface. We've got an inner metal. And we've got liquid coolant in between, so it's -20, so pretty cold. And then we've got the mixture we're using, okay, that we're making ice cream with. Okay, the bowl causes the mixture to cool down and freeze, so it starts off being a liquid, and we solidify it. Your question is, explain why the different thermal conductivities of metal and plastic are important in the design of the bowl. Okay, and here's the student's answer. You need to fix it and correct it. Pause the video here. Okay, so moving on. The metal is a poor insulator. It's not enough. Okay, you need to reference what the thermal conductivity is. You need to say if the metal is a good insulator. No, it's a good conductor. Okay, or a poor conductor. You'll need to focus on what it's giving you in the question to help you answer. Explain why the different thermal conductivities. You have to use that jargon, that scientific language to get the answers. So the metal has a high thermal conductivity that increases the rate of energy transfer. So the first mark is for it's got a high thermal conductivity. The second for it increases the rate of energy transfer. The plastic has a low thermal conductivity. This reduces the rate of energy transfer. If you talk about insulating, if you say that the plastic is a good insulator, you don't get the marks. The marks team says ignore insulation. Okay, the question specifies, it says why in terms of its thermal conductivities. Okay, Next, why did the student only get 2 marks? So each time a student does 1 chin up, he lifts his body up 0.4 meters vertically. We've given the mass of the student. He's able to do 12 chin ups in 60 seconds. We've got the gravitational field strength of 10 newtons per kilogram. We need to use the right equation. Why did the student only get 2 marks? Find the mistake and fix it. Pause the video here. Okay, next. Okay, so look, 12 chin-ups. At no point do I work out what that 12 extra chin-ups would be. I've worked out just the energy, or sorry, then the power for a single chin-up. So if we're doing 12 chin-ups in 60 seconds, we know that the change in gravitational potential energy, that one lift is 260. The total energy change, the total energy transferred, will be 260 times by 12. Okay, that gives us 3,120 joules done in 60 seconds. So we divide by 60 to get 52 watts. Okay, so be careful. Read the question 3, 4, 5 times. Okay, this is the kind of mistake that you can also pick up at the end if you have time to check answers. Okay, check that you've used all the numbers and make sure you need to. Okay, next question. Why did the student only get 1 mark? So the energy transferred from the water in the kettle surroundings in 2 hours is 4,200 joules. Use the correct equation from the equation sheet. Okay, where's the mistake? Can you fix it? Pause the video here. Okay, so this question, they didn't convert the units, not properly. They changed the 2 hours into minutes instead of seconds. Okay, you need to make sure that you convert the units correctly. There will be at least one place where you have to convert units on your paper, at least once. I think because you're given the equations that there are going to be more than one places. They're going to test that skill in more depth than they would in other years. Okay, so make sure you look for the question that tells you you need to convert the units. You should not use hours, you should use seconds. You should not use kilojoules, you should use joules. Okay, be careful and make sure you correct for those units. Okay, next we've got a number of different resources for energy generation, for generating electricity. Okay, which are renewable? What does renewable mean? What are some advantages and disadvantages of each? Okay, pause the video here. This could take a little bit of extra time. Okay, so be aware. Try and get at least one good and bad thing about each of these types of electricity generation. Okay, so make sure it's paused now. Okay, so which are biofuels? Which are renewables? Biofuels, wind, hydro, geothermal, tidal, solar, and waves, all renewable energy resources. A renewable resource means that it is replenished at the same rate it is used. Okay, if it is replenished at the same rate it is used, it will not run out. But AQA do love the word replenished when they're talking about renewable energy resources. Now, as for advantages and disadvantages, there are lots. Okay, so for fossil fuels, there's a chemical energy store. It's non-renewable. We've got some uses: transport, heating, electricity generation. It's got a high power output. Okay, it generates a lot of electricity for not much fuel. It does release CO2. Note the 2 is subscript. Make sure it's at the bottom and not the top. That will drop you a mark. Okay, it does cause global warming. Okay, climate change. We've got nuclear. It's non-renewable. Lots of people forget that it's non-renewable because it's not a fossil fuel. But there is only a limited supply of radioactive material that we can use to generate electricity using nuclear. There is a lot. Okay, but it is non-renewable. It has an incredibly high power output. You don't need much fuel at all to generate a tremendous amount of electricity. It does have a big environmental impact because it produces radioactive waste that needs to be disposed of safely, which can cost a lot of money. Biofuels, energy storage chemical. It is renewable. Okay, you can use it in transport, heating, electricity generation. It's got medium. It depends on how it's used, but a medium power output. It is carbon neutral. So you will grow trees. You will chop the trees down. You will burn the wood. You will grow new trees. So you are putting carbon into the atmosphere when you burn the wood, but you're taking it back out when you grow new trees. Okay, so it's carbon neutral. It won't increase the amount of carbon in the atmosphere. Wind, Energy store is kinetic. It is renewable. Okay, we generally use it for generating electricity. You can have windmills where we're making flour and stuff like that, but electricity generation is the biggest part of wind now. It has a low power output for a single turbine. You need lots of single turbines to replace a single fossil fuel power plant. So it takes up a lot of area that could be used for farming and other bits and pieces. Some people do say it spoils the view. Okay, a bigger impact is, or a bigger negative, is that it is unpredictable. It's very difficult to predict in advance how much electricity you'll get on a given day in the year. You don't know the weather. It's weather dependent. Hydroelectricity, it's renewable and generates electricity. Local habitats can be affected because there'll be areas of flooding where we store the water, which has that gravitational potential energy. Okay, it is more predictable than wind because we know how much rainfall there's going to be, and we keep that store of energy. So we know how much energy we've got stored in the water that's lifted up high. So we know how much electricity we'll be able to generate with it. So it's quite predictable. Okay, but it does damage those habitats. Geothermal has a very low impact in terms of environmental impact. You're just digging a big hole into the ground and getting hot water from it. Okay, doesn't generate that much power. The issue with geothermal is it will only work effectively in certain places in the world where you do have hot rocks close to the surface of the earth. Tidal energy, tidal barrage can block sewage which needs to go out to sea. You'll only generate electricity at given times in the day, so when the actual tide is moving is when you'll generate the electricity, so you can't use it solely to generate electricity. It could give out a lot of energy, but it's very dependent on location in the world, so only where you'll be able to harness the actual tides you'll be able to get it. Solar and the sun, it's heavily dependent on the weather and only works during daylight hours. It won't work during nighttime. Okay, it's a low environmental impact. It does take up a lot of space, quite a high startup cost. Water waves, you generally don't get that much electricity power output from getting energy from water waves. So it's got a low power output. It is renewable, doesn't give out emissions. It's got a low environmental impact. Now, next, we've got a table of information. We've got coal, gas, oil and wood. We've got the emissions per kilogram in megawatt hours. We've got the life cycle and CO2 emissions in kilograms per megawatt hour. Okay, now we might not have come across those units. You might get information that you haven't ever seen before. These are the really difficult questions that you've got to really think about and use what you do know to try and answer. Okay, so this is just saying how much CO2 we get by burning a certain amount of energy, by using a certain amount of actual electricity output. This is how much carbon I get out. Okay, so direct CO2 emissions is the amount released when the fuel is burnt, but the life cycle also includes it when it's extracted, maybe building the power plants, all the rest of the information. So we're using the table to explain why wood is considered to be a low carbon dioxide emitting fuel. Okay, so nice quick one. You need to try and fix the mistake. Pause the video here. Okay. What is meant by a non-renewable energy resource? No. The source cannot be reused. That's not correct. No source can be reused. The energy resource cannot be replenished as quickly as it is used. The energy source will run out. Okay? The energy source will run out. Next, I would like you to try and write as many units for each of these quantities as you can. So what do we measure energy in? What do we measure mass? What do we measure speed in? What are the units for these? You will be asked to write down units in some of your questions. At least once, probably more than that, you will have to write down what the unit you're using are. Now, because you're given the equations, like just for the conversion of units, I think you'll be asked this more often than you would in other years. Okay, so as quickly as you can, try and write down as many of the units as possible. Pause the video here. Okay, so all of my highlights are types of energy. All energy is measured in joules. Okay, so zoomed in, a little bit easier to see. All of my energies are in joules. So kinetic, elastic, gravitational, thermal, energy transferred, work done, all measured in joules. mass in kilograms, spin constant, newtons per meter, extension in meters. We've got height in meters, gravitational field strength in newtons per kilogram. We've got power measured in watts. Now for spring constant extension, sometimes it will be newtons per centimetre and centimetres. Okay, but we tend to use metres. Next half, we've got efficiency with no units. My joules for my energy output and my energy input, they cancel each other out, just like for power and power here. Those units cancel, so efficiency does not have a unit. We've got charge flows measured in coulombs, current is in amps, times in seconds, potential difference in volts, current in amps again, resistance in that funny horseshoe unit called the ohm, power in watts, and that's all of them. Next job, okay, we need to convert these into standard units. So what would 800 kilojoules be in joules? What would 12 kilometers be in meters? So pause the video here and try and convert as many of those as you can. Okay, so moving on. So kilo times by 1,000. So 800 would be 800,000. Okay, same for kilometers. Giga, okay, times by a billion. Divide by 100,000. Divide by a billion. Divide by 1,000. Times by a million. Okay, so here are my converted units. Okay, our next job, okay, and final slide before I wish you luck, is converting these into standard form. Now you can do this with your calculator. Okay, you can ask your teachers to try and help you and try and convert from normal decimal into standard form and back, but I'd like you to try and convert these all into standard form. Pause the video here. Okay, so answers. Okay, we've got all of these answers in standard form. Now what you can do, if you know what the standard form is of each of these conversions, you can just times it onto the end and that gives you the right answer. Okay, that's the way I convert my units from the changed versions into the standard way. Okay, now I hope you have a good exam. I hope it goes as well as possible. I hope this was helpful. The parts of it that was helpful, can you please let your teachers know so we can either replicate it for the next masterclass or change it so it is better for the next one. Okay, so best of luck year 11. You're going to smash it. Well done.